we've looked at molecular diffusion in gases where the Fick's law was developed. We looked at the equimolar, unimolecular. Then we also applied the same to liquids in diffusion, to diffusion in liquids, and this is where we found out about the average concentrations and how to calculate it. And we now want to look at the molecular diffusion in solids, where we have already said that diffusion in solids is slow due to close packing of particles. So the rates of diffusions are generally slower in gases, in solids, but this transfer of mass in solids is quite important in chemical and biological processes. And some of the example here, we're looking at leaching of foods such as beans, soybeans, and of metal oils, drying of timber, salts and foods, diffusion and catalytic reaction in solid catalysts, then separation of fluids by membranes, diffusion of gases through polymer fumes used in packaging, treating of metals at high temperature by gases. So this diffusion is not dependent on the actual structure of the solid, but you would find that this diffusion occurs when fluid or solid diffusing is actually dissolved in the solid to form a more or less homogeneous solution. For example, in leaching, where the solid contains a large amount of water, and the solid is diffusing through this solution, or in the diffusion of zinc through copper, where solid solutions are present. You can also look at the diffusion of nitrogen or hydrogen through rubber, or in some cases, diffusion of water in foodstuffs. Right, let's look at the derivation of the equation. So that is the general equation. NaYAN minus C dAB dy over dz. Please note that this is equal to Na plus Nb but this term, the bulk flow, we have it there, is usually so slow due to YA. So it's neglected. So this is neglected in most cases. So there C is a constant. So diffusion of solids is then given uh, basically by that equation. This gives us diffusion of solids, which would need to be integrated and find the equation. So your DAB is diffusivity in meters squared per second of A through B, and usually is independent of pressure for solids. So DAB is this should be equals GBA in solids there. So integrating the equation there through the limits CA1 to CA2 and Z2 to CA1, we get this as the integrated form to get our flux. So we can also look at that equation through a hollow cylinder there, where you remember that kgs per second there divided by the area, then this is equals to minus DABGCA, which we also need to then to integrate. But pay particular attention to this, which is the surface area of our hollow cylinder, and that's how it's calculated. Then we look at instead of Z we have dr, which is characteristics on that one, as you would see there. So integration of that over the limit CAI to CA naught and R naught to RI. So remember our R there, R naught is the outer radius, RI is the inner radius, L is the length, CAI is the initial, CA naught final concentration. So this is similar to conduction heat transfer radially through a hollow cylinder. Is seen on this picture there. So there where we are talking about the mass transfer per time, then the mass transfer per area per time, which is our flux, then the area of mass transfer. So we can find the concentration profile, but only up to an arbitrary radius r and the concentration C at that point, is indicated on that one. In the equation shown, so this is what is integrating to an arbitrary value, and this is R, CA, and our R there. Moving on, then we've said that Na is a constant. So our CAR is equals to, after the integration there, CA1 minus CAI minus CA naught to get that value. So we can use this now to draw our concentration profile. So steady state diffusion through a spherical cavity. So you're looking at that diagram there, the spherical shell, and going back again to Na over the area, which is 4 pi r squared, which we will then again equate to minus dAB GCA over dr. Then after integration, we get the value. So this is what we get after the integration there. Then with that, so diffusion in solids. As earlier on alluded, this diffusivity or diffusion coefficient in the solid is independent of pressure of gas or liquid on the outside of the solid. So just for an example, if our gas CO2 is outside the slab of rubber and is diffusing through the rubber, DAB would be independent of PA, the partial pressure of carbon dioxide at the surface. But what is important is the what is termed the solubility of CO2 in solid, which is proportional, which is directly proportional to PA. So again, this is similar to the case of solubility of O2 in water being directly proportional to partial pressure of oxygen in the air as given by Henry's law. So looking at the solubility of solid gases in a solid, right? So let's define something. So our solubility is indicated by S in meter cubed per solid, per meter cubed solid, per atm pressure. Then for us to then convert this solubility to concentration in solid, we use the following equation, which is Ca equals to Sm cubed. Then we divide that by 22.414, or SPA over 22.414 is indicated there. So that can be done in CGS units again as 1.5858. Let's look at an example where diffusion of